So far we've introduced logistic regression. We found that using the logistic transform, we can make sure that our predictions lie between 0 and 1. But that's not all we need to do. We need to think about the loss function that we're going to minimize when doing logistic regression. What we were doing up until now with Amy's house pricing was using a loss function which was the mean square error. You might remember that our performance metric was mean absolute error. Now let's think what happens if we use the squared loss for logistic regression. When the actual is 1 and the prediction is 0, the error is 1. To be precise, it's 1 minus 0 squared. When the actual is 1 and the prediction is 0.5, then we're going to get an error of 0.25. And when the actual is 1 and the prediction is 1, the error is 0. When the actual is 1 and prediction is 0, you can see that our error is 1. Is that enough for being 100% sure about the wrong outcome? It doesn't feel enough. You can see in the middle where we were 50-50, we had a contribution to the loss function of 0.25. But to be 100% sure and to be completely wrong, I kind of feel that we need an addition to our error function of more than 1. Let's go back to good old probability and think of the binomial distribution. Do you remember the binomial distribution? You would choose y things from n. The probability of choosing y things from n depended on the probability of just choosing one thing, but if you knew what it was, then the probability would be equal to n choose y, p to the y, 1 minus p to the n minus y. And that's what we have here, just forgetting the binomial coefficient. If we take the log likelihood, so we're just going to take the log of the binomial likelihood, we're going to get the log likelihood as proportional to y log p, n minus y, log 1 minus p. It's going to be easier for us if we consider just one example. So this n over here is going to turn into 1. And we end up with, for one example, the log likelihood proportional to y log p, 1 minus y, log 1 minus p. Statisticians tend to fit models by maximizing the likelihood. So what they would do is try to maximize this thing over here. Now, instead of maximizing this log likelihood, we could minimize minus this function. Why would we want to think about this in terms of minimizing it? Because in machine learning, we always think about minimizing a loss function. So let's put a minus in front of this and call it a loss function which we want to minimize. Here we have it. Here is a proposed loss function. If we minimize this loss function, it's exactly the same as maximizing the binomial likelihood. In machine learning, this function, this loss function, is called the log loss. And once again, we have a link between machine learning and good old-fashioned statistics. Let's have a look at the log loss. In these various cases, where the actual is 1 and the prediction is 0, you're going to get minus 1 times the log of 0. The log of 0 is a massive negative number. Minus that is a massive positive number. So for being very sure and being totally wrong, you will have a loss close to infinity. Saying that probably made any mathematicians amongst you cringe. How about perfection? 1 and 1, do the maths, and you'll see that you get a loss of 0. And somewhere in the middle, well, 1 times log of 0.5, I don't know what that is, but it's somewhere in the middle. I know you're thinking, why on earth are you doing this? You promised us no theory whatsoever. It's just really hard not to give a little introduction as to what is making logistic regression tick. I do think it is so beautiful how the language of loss functions used in machine learning translates directly from good old-fashioned statistics. We find a very similar thing which we haven't really covered in penalized regression. The penalized regression is in some ways a simplified form of Bayesian regression using different priors, for example using a Gaussian prior with a mean of 0. Anyway, enough about that. You were probably confused enough already before I said that. Where does that leave us? 3 things. If we're talking about logistic regression, we are talking about a linear predictor that you see in front of you, B, a logistic transform, where the prediction is e to the eta over 1 plus e to the eta, and finally, what we do once we have those 2 things set up, we ask our computer to minimize the log loss function, which is given in front of you. Enough of that. We're going to head straight over to H2O, and we're going to try and solve the Titanic with logistic regression and elastic net. Here we go.